Right, so the briefest of introductions today into magnetic resonance hardware. Of course, the module is not intended to be a course in electronics or radio frequency engineering, but for us to meaningfully go into the dynamics of spin, the construction and analysis of pulse sequences, into the digital signal processing of NMR data, we need to understand, at least superficially, what goes on inside the instrument. You've all seen NMR spectrometers, hopefully by now, so a giant magnet and a console the size of this drawer next to it, filled with electronics, amplifiers, computers, and so on. So let's have a brief glance into what is going on inside. So item 1 on the agenda is the magnet. And you've seen the diagram in the previous lecture, but it may have left you wondering how on earth would one put 200 amps per square millimeter into a loop of superconductor. If it's a loop, if it's superconducting, how do you generate this kind of current in it? Because of course any device that you would plug into a superconducting coil, the current would just go the shortest possible way, right? So it's not immediately obvious how one would put a circular current into a superconducting magnet. The way it's done is we take a look at our magnet coil. So there's a loop here. We cool it to about 4 Kelvin, so the liquid helium temperature. We connect a power supply, so there's some voltage across these terminals. But what we also do to prevent a short circuit here is we warm up this particular region to above the critical temperature of the superconductor. So everything is at around 4 Kelvin, 4.2 Kelvin to be precise, the boiling temperature of liquid helium at atmospheric pressure. There's a power supply that's attached here, and there's a little heating coil in here that keeps this segment above the critical temperature of the superconductor. So there is virtually zero resistance across this entire magnet coil, but there is a finite resistance across this little segment. So what is then done is we turn on the power supply. And although the resistance across this coil is virtually zero, the coil has a colossal inductance because there are so many loops of wire in that and quite a lot of metal around it. And if you remember your undergraduate electrostatics and electrodynamics, it is not possible to ramp the current up in a coil with a finite inductance because the magnetic field would be infinite through it, so it would only permit the current to be ramped slowly. So even though there is no resistance, there is something called impedance that prevents a short circuit here. So what is then done is we slowly ramp up the current through the magnet by keeping this voltage source operational. We have a magnetometer. We wait until the field is ramped to, well, it depends on the actual magnet, but between about 5 Tesla and 28 Tesla these days, depending on which induction it can survive and which kind of current. And then in the final step, the heater here is switched off. This little gap becomes superconducting. The power supply senses a short circuit and disconnects, but of course the magnet has accumulated enough of a magnetic field and there's enough of an inductance that the current keeps going. And so now that the entire loop has been cooled to 4.2 Kelvin, there is an indefinite circulating current through that superconductor. Now, of course, nothing's ever perfect in nature, but this is as perfect as they come. The resistance is so incredibly close to zero that the current can keep circulating for years and decades in it. The amount that is lost per day due to just external electromagnetic noise and tiniest amounts of residual resistance in there is about 10 to the minus 6 to 10 to the minus 7 of the total. So if you have a magnet with the Larmor frequency of 600 megahertz, the typical daily drift that you would see in a good magnet is, you know, a few tenths of hertz, a few hundreds of hertz. If the magnet's really old, maybe a few kilohertz. So tiny fraction easily compensated by, for example, a resistive coil that's wound around the probe that you put into that magnet. So the losses of the current and the losses of the magnetic field inside this thing are actually pretty much negligible, certainly in modern superconductors. Of course, what we need to do is make sure that the thing stays cold. So there is a reservoir here of liquid helium. Then there's vacuum. So there's a chamber that's been pumped out to keep the heat insulation. And then on the very outside we have a liquid nitrogen chamber, so N2, and then on the outside again there is another vacuum chamber, and then the outside steel hull of that magnet. So as you know, this is 70 Kelvin, so this is vacuum, and that is vacuum again. Designed to maintain 4.2 Kelvin around that coil for as long as possible, as well as possible. Still, of course, we are at 300 Kelvin, or well, at the University of Southampton we are at something like 295 Kelvin most of the time. But these cryogens do slowly evaporate. Typically we need to top up the liquid nitrogen here approximately once a week. There's a nice rolling timetable of all the PhD students who have to do the nitrogen filling duty on those magnets. They seem to enjoy it, but I've been bored a long time ago. And a somewhat more interesting task of filling in the liquid helium roughly once a month. Now, it gets evaporated. If it's not recirculated, somehow it ends up in the atmosphere and of course is thereby lost. Typical magnet boils of about a liter of liquid helium in a fortnight, in a week or thereabouts. Not a negligible amount, because liquid helium costs about as much as a good whiskey these days, so about 50 pounds a liter. In liquid form, so not something to be sneezed at. And of course the major manufacturers of liquid helium are located in various places that are not necessarily friendly to this country, namely the Middle East and Russia, because helium is chief byproduct of radioactive decay in the Earth's crust. So remember, alpha particle is the helium nucleus. So something decays, produces an alpha particle, it gets stopped somewhere in the ground, grabs itself a couple of electrons, becomes helium, and goes to the nearest gas reservoir it can find, which is pretty much the local reservoirs of natural gas. So most natural gas locations on Earth have close to 1% or thereabouts of helium in them, and it's easily separated, liquefied, and shipped to us here. But at the moment there's a bit of a crisis going on, because the American government hasn't exactly been wise in selling its strategic reserve of helium, because the prices it has created have just put every manufacturer out of the market. And it's done so repeatedly, so there's a certain amount of turbulence in liquid helium market at the moment. And from the fact that I'm watching the market prices for liquid helium, you can tell that that's kind of important, right? Because every MRI instrument in every hospital, every NMR instrument downstairs, I'm a theorist, I don't strictly speaking care, but looking at the pain at the faces of all the experimentalists can be shocking sometimes. Okay, so that is the magnet and how it is energized. Once it's energized, it just stands here. There's a giant hole at the bottom, well, giant, 35 millimeters, into which the probe goes, and most of today will be about the probe and the electronics that is driving that probe. So item 2 is the block diagram of the electronics. All of it starts with a computer. It always does these days. So we have a computer. And there are 2 branches in every NMR instrument. There is the transmit branch and the receive branch. And the difference is by about 12 orders of magnitude in the power that goes in and out. When we operate the instrument in the transmit mode, our task is to create as strong an electromagnetic field as we possibly can. We want the spins to nutate around those fields rapidly. So we are dealing with kilowatts of radio frequency amplitudes. However, at the detection point, nuclear induction signals are exceedingly weak. They are microwatts or less. And so we face the interesting problem of using the same electronics that we've just used to transmit a kilowatt into it to detect a microwatt that is coming out. Okay, so on the transmit side, we have radio frequency synthesis. So RF has an exact name for that thing. Forgive a mathematician, is RF pulse generator. It has 2 things: a very precise clock that enables it to output a very stable sinusoidal wave. And stable, I mean that the phase of that sinusoidal wave can be maintained on the time scale of hours. So we have a clock that generates a sinusoidal oscillation at the frequency of about a gigahertz or thereabouts, so a billion oscillations per second, and the phase stability is such that the peak of this wave stays at the same place on the time scale of hours. So you can see it is actually a rather precise toy. Then the second thing that this has is a device that can turn this output on and off, right? That can chop out the periods here of around 1 to about 100 microseconds. So there is the precise RF synthesis circuit and a very precisely timed circuit that can turn it on and turn it off to generate the radio frequency pulses, which we will later use. That goes into the amplifier. So at this point, this is milliwatts. At the output of the amplifier, this is kilowatts. That goes into a device called duplexer. And the purpose of this device is to very precisely route the incoming and outgoing signals. The reason that is necessary is the instruments use the same coil for transmission and reception. And so here, on the output of that duplexer, there's a capacitor and there's the probe circuit, which is roughly representable like that. So we've got a resistance. Any material at room temperature would have a resistance. We have an extra capacitor and we have our radio frequency coil, which is acting as an inductance here. So R, L, and C. Now, whatever goes in, the duplexer routes into the probe. Whatever comes out of the probe, the duplexer routes to the detection circuitry. But this amplifier is very well insulated from the detection circuitry here. The reason for that is what comes in is a kilowatt. What would come out of the duplexer here is a microwatt. If the preamplifier here accidentally sees a kilowatt, that will be the end of this preamplifier. All right, expensive pieces of circuitry. So what is here is a preamp. An amplifier, sometimes cryogenically cooled to reduce the amount of noise that it has, but narrowly optimized for exceedingly weak input signals. So we are operating these devices typically at the quantum mechanical limit of the electron noise in the conductors. So when electrons move, they get scattered on the nuclei, they are perturbed by phonons in the solid materials. There's of course the standard Boltzmann amount of noise at a given temperature. So typically these devices operate at the limits imposed by fundamental physics on how much noise you can have in there. So from the preamplifier we go into a band-pass filter. Normally, of course, the noise in electrical conductors would have a certain distribution of frequencies, and those distributions are known. However, we do know which nuclei we are observing. We do know the corresponding Larmor frequency, and so it makes sense to create a device that allows certain frequencies to pass and stops certain other frequencies from passing, because that would destroy a lot of the noise that is sitting in some other frequencies that we have. So these band-pass filters, they just chop out a certain frequency range in which we are interested, and they stop all other frequencies from going through, which reduces the noise. Okay, then we have a second amplifier. This one is reasonably conventional, because the preamp has already preamplified us from microwatts to perhaps milliwatts or watts. This amp goes into a little device that reads the analog voltage that you have here and digitizes it. Simply speaking, converts it into a number. So ADC, analog to digital converter, and then there's a digital link, typically just an Ethernet cable that connects back to the computer, and we get the numbers coming out that we can then do mathematics on. So to repeat all of that from the beginning to the end, the computer gives a digital instruction, so that is again an Ethernet cable typically here, to the RF pulse generator, which contains a precise clock signal and a modulator that chops it off. Signals here can be shifted in frequency to some extent. I will not go into the details of how that is done, but it can be done. This is amplified to the maximum power that is permitted by the circuitry here. Remember, the size of this coil is about 0.5 centimeter in width and about 2 centimeters in height. The size of these capacitors are in the millimeters, and so if we put too much charge across this capacitor, the electric field will be strong enough to just puncture through the dielectric, or there will be arcing in the coil, and so there are limits to how much power we can put in, but we operate pretty close to those limits usually because we want as short and as powerful a pulse, as you'll later see, as we possibly can accomplish. So that goes into the duplexer, goes into the coil. That's our tuning and matching capacitor. I will tell you what it is in the next section of this. Whatever nuclear dynamics needs to take place in the sample that is inside this transmit and detect coil takes place. We get into the detection period when the amplifier is blanked and the duplexer routes our incoming signal into this preamplifier where it's amplified somewhat, then through the filters, then into the final amplifier that gets the voltage up to a level that an ADC can comfortably digitize, and all of that goes into a computer. In the last few years, this has all been really miniaturized quite well to a point where there are labs in the world that do this on Raspberry Pi. There are software-defined radios these days that can do it. Of course, the amplifier here and the preamplifier have to be purchased, and they're sizable, but the rest of the electronics is really miniaturized quite a lot. But in my time, when I was a PhD student, that was a good £500,000 and a rack of electronics that was quite substantial. Okay, so here I would like to hide most of the complexity from you, and I did. What we will now need to consider in some detail is this circuit, right, the RLC, because a lot of what we are going to do in the subsequent lectures will involve this circuit. So all of that is the electronics you can buy off the shelf. This, however, is something we need to understand in some detail. So item 3 on the agenda, RLC circuits. So 3 RLC circuits. Okay, let us redraw that thing with a few details missing. So we will consider a circuit like that. It will have a resistance, it will have an inductance, and it will have some voltage source here. And that will be it. So we have capacitance here, resistance here, and inductance there, and voltage. I'm aware of the fact that you are chemists, so none of you had any circuits or radio frequency electronics, not maybe even at school. So we will go very slowly and carefully through how these things are made and analyzed until we obtain a differential equation, at which point you know what to do with that, because hopefully you've been taught how to solve it, perhaps even by me. I don't remember. If you've been in 1047 and 2024, then I had taught you how to solve differential equations, and that is why I was torturing you with them, because this time I knew would come. Okay, so let us take a look at this and think as electricians do. So the first thing we need to consider is the fact that if we go the entire loop across this circuit, then the total change in the potential across this circuit must be 0. Right, easy to understand. If I cut the little slice in here, for example, and I look at the change in the potential across the little tiny slice, it is of course 0, right, or close to 0. But the same must be true if I go the opposite way around, because the functions are continuous that describe this potential as a function of location. And so any loop integral of voltage across any closed circuit must be 0, which means the following must be true. Whatever voltage our source here puts out must be exactly counterbalanced by the rest of the circuit. And so we have our voltage at the source possibly as a function of time. We don't know what it is, we don't want to know. But what must be true is the sum of voltages across the other three elements must be exactly equal to that. So the voltage across the resistor voltage difference plus the voltage difference across the inductor, likewise for the capacitor, must sum up to exactly the same amount as the voltage of the source. This is called Kirchhoff's voltage law. Okay, nothing supernatural here, makes sense. Part B, if we look at that circuit, we can say, well, okay, these are all copper wire, occasionally even gold, and the only significant resistance here is probably the resistor, which is intended to be a resistance. And of course, across the resistor, we simply have the Ohm's law, right, that the voltage is related to the current by the resistance. And so the voltage across the resistor must, of course, be the resistance times the current. And the current is common for the entire circuit, as you know, because of the conservation of charge. Whatever current I have through the resistor, I must have exactly the same current through the inductor. Okay, Ohm's law. So far, so good. Then there are two laws that you might not have been taught at school, depending on whether or not you did further physics in your A levels. So if you did, you'll recognize them. If you didn't, take my word for it. So there's something called inductor equation that says that the voltage across the inductor is the function of the derivative, the rate of change in the current. So inductance times I prime of t, and it's called inductor equation. So this is the voltage across the L. And you see what I'm doing, right? I know the voltage across the source because I control it. So voltage across the resistor, I'll put this there. Voltage across the inductor, I'll put that there. And you see that's a function of current, that's a function of current. Now I need one last thing, the voltage across the capacitor as a function of current. Then I will have current, 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 and I have the equation of motion for the current, almost specifically for the charge, as we will see. So the final equation that we need, well, no, not the final, there will be more. So equation D relates to the capacitor. And that is that the current across, well, not quite across, but the current flowing into the capacitor is capacitance times the derivative of the voltage. So the rate of change in the voltage. So, but okay, I still have the VC that I can use to replace that here. So that is the capacitor equation. Now the final thing is to note that current is the derivative of charge. Right? So I of t is actually dq by dt. In this case, we can take the charge on the terminals of the capacitor as the charge we're interested in. So what we are going to do now is to pile all of that in. Let's see what we are going to have, and we will express it in terms of charge. So I is dq by dt. So if I put it here, I will have dq by dt, first derivative. See the I prime in here, so that will be the second derivative of this charge there. Then the v prime c will get integrated, and this will go here, so that will be the charge itself, right? So if that is the derivative, then the derivative of the charge goes here. Integrate both sides, Vc will be proportional to the charge. Once we put all of that together and simplify the arithmetic, we will get a rather nasty looking non-uniform second order differential equation. All of that comes out into d2q by dt squared plus r over L dq by dt plus 1 over LC q of t equals 1 over L source voltage as a function of time. So you can see we have the second derivative that came from the inductor equation, we have the first derivative that came from Ohm's law, and we have the no derivative that came from the combination of capacitor equation and the definition of charge. And it's being driven by the voltage source. I assure you that you don't want to see me solving this equation in full generality. It is painful. So let us take a look at a few simplifications. So simplifications. Let us first disconnect the voltage source completely, just bridge it like it doesn't exist. So nothing is going to be driving our circuit. And let's remove the resistance. So we will only keep the capacitor and the inductor, and we will start the circuit in a state when the capacitor is charged. So what is going to happen? The capacitor will start discharging itself through the inductor. Magnetic field will accumulate here, as you know, will magnetize some material in there. Then the capacitor will get discharged, but because the inductance here, the current will be generated as a result of the magnetic field changing in here. So it will recharge the capacitor in the opposite polarity. The capacitor will then begin discharging again. So the usual oscillating LC circuit. So let us do it mathematically. We have d2q by dt squared. We had put resistance to 0, so plus 1 over LC q of t equals, we have disconnected the voltage source, 0. Well, that's a much easier differential equation, isn't it? Although still quite beastly, because of course it's a second order one. Let us move the q over LC to the other side. d2q by dt squared is minus 1 over LC q of t. And you probably remember how we solve ordinary differential equations. We just introduce an ansatz, an exponential. We put it in and we find out which exponents satisfy this equation. So trial function e to the lambda t. We put it in and we find out which lambdas fit. So d2 by dt squared e lambda t equals 1 over LC e to the lambda t. Second derivative here pops out lambda square. So we are going to have lambda squared e lambda t is minus 1 over LC e lambda t. E to the lambda t cancels. We get the equation for lambda. From there, lambda squared is minus 1 over LC. You can see the solutions are complex. So lambda is plus minus I over root LC, which tells us that our solutions are complex exponentials or equivalently sines and cosines. right? And that was one of the last lectures in, I think, 2024 mathematics module, when I had told you that in such situations the general solution Q of t is some arbitrary coefficient times the cos of this lambda t, so 1 over root LC t plus some other arbitrary coefficient times sine 1 over root LC t. And we can easily find the particular solution. We can say, well, okay, we expect our initial charge at some starting point to be equal to 1 and the derivative to be equal to 0, and that would give us the coefficients a and b. But what we want here is to observe the particular frequency at which the circuit naturally oscillates. It's 1 over root LC. And this is called omega naught, and it has a name. It's called the resonance frequency of the circuit. So that is the frequency at which circuit oscillates if it is left to its own devices. If we look here, this capacitor and this inductor, let's think about them from the electrical point of view. The coil of the instrument has a fixed geometry. Somebody has wound that coil, soldered it in, and that's it. It's a given. We cannot change the coil geometry, we cannot change the number of turns, so this inductance here is a fixed number that we cannot do anything about. Capacitors, however, are quite commonly tunable. That's the sign for a tunable capacitor. We can simply just withdraw a little bit of dielectrics in between the two planes of that capacitor, or change the dielectric and so on. So the capacitance we can actually tune, which means that we can tune the resonant frequency of that circuit to match the Larmor frequency of our nuclei. If we are dealing with, say, 600 megahertz, so protons at 14.1 Tesla, and our electronics engineers have created us a coil with a suitable inductance, then there's a tiny rod sticking out of the probe at the bottom of that magnet that adjusts this capacitance, and we adjust it until we bring the resonance frequency of the coil to match the resonance frequency of our nuclear spins. Now, I will not go through the mathematics here of what happens when we turn the resistance on. There's always a certain amount of resistance in the probe, and I will not go through the mathematics of what happens when we begin driving that coil with this voltage. Let me just say that if we have the resonance frequency of the circuit matching exactly the frequency at which it is driven, then that is the best possible case. We produce the greatest possible oscillating magnetic field in the inductor, and we have the greatest possible sensitivity when the magnetic field arrives back from the nuclei, and it's all getting amplified and converted into these signals here. So I think this is as much as I wanted to say about this particular tiny circuit. Notice that there's a further capacitor in here. So this is called a tuning cap for the reasons that I've just described. This is called a matching cap. And you will actually see two rods sticking out of the probe, one for the tuning capacitor, whose role you now fully understand, and one for this matching capacitor, which I really don't have the time within 45 minutes to discuss in detail. To wave my hands a little bit here, the role of this is to match the impedance, so the complex resistance of this circuit to the impedance of the rest of the instrument. That simply makes sure that whatever radio frequency voltage we put in flows into the circuit without reflections. So if the frequencies mismatch, then there's a certain amount of reflected signal, because of course, strictly speaking, this is not a continuous conductor, right? It will only conduct oscillating current, but never the direct one. And of course, our preamplifier has to be protected as much as possible. And if we push a kilowatt into there and much of that kilowatt bounces back, then that's not a good idea for this preamplifier. So this matching capacitor is there to make sure that nothing is reflected from that probe circuit when we are issuing the excitation pulses there. And of course, as you can imagine, in real life, this is all a lot more complicated than these simple diagrams. There are various stray inductances because lots of the other probe parts are also made of metal. There are stray capacitances because some wires can be close by, and that creates a capacitance you knew nothing about. And so the task of designing and modeling these probes is so complicated that companies exist and have existed for decades that manufacture those probes. And a typical NMR probe is between 30 and 200,000 pounds, depending on the complexity. If those toys were made out of solid gold, they would have been cheaper. Right, so that is the level of complexity and skill that goes into the manufacturing there. Okay, I think that's as much as I wanted to say in this lecture. We go into the quantum mechanics and the more conventional magnetic resonance from the next one. But essentially, we have a magnet, a giant superconducting coil, and it's energized in a rather interesting way by keeping a segment here with finite resistance, by heating it, injecting enough current to bring the magnet up to field, and then just cooling that segment down until it becomes superconducting and disconnecting the power supply so that the current keeps circulating in the magnet. Our computer gets instructions out to the RF pulse generator. The pulses get amplified, duplexer sends them into the circuit. We tilt or otherwise manipulate the spins as a result. That's the subject of the next few lectures. Then as soon as we are done tilting, we let them evolve. Oscillating spins create oscillating magnetic fields. Oscillating magnetic fields create voltage across the inductor. That voltage propagates through the circuit, duplexer routes it into the preamplifier, it's preamplified, filtered by the bandpass filters, which are themselves RLC circuits of that kind, amplified, digitized, and returned back to a computer. And finally, the mathematics and physics of RLC circuits is easier than one could think. We simply use a lot of common sense on the Kirchhoff's law for the voltages, Ohm's law across the resistance, and two similar equations called inductor and capacitor equations that just relate the current and the voltage across the inductor and the capacitor. We put them all together, introduce the definition of current as the derivative of the charge. After all of that is brought together and simplified, we get the equation of motion, which is a second order differential equation. Has nasty solutions. We study them in chemical engineering, so chemical engineers do get the full electronics module where we do that. But to just demonstrate that the thing oscillates and resonates, we can simplify it by putting resistance to 0 and disconnecting the voltage supply, and then just starting with a charged capacitor and watching the current wobble in it. That leads to a simplified equation, which we do know how to solve from our mathematics module. We put the trial function in. We realize that the eigenvalues are complex. That tells us that these are complex exponentials, but of course the current is a real quantity and the charge is a real quantity. The only way to make these things real is to break them up into sines and cosines using Euler's relation, right, for the complex exponential. And so the general solution is a cosine and a sine of this number times time, so that has the physical meaning of frequency, and this is our resonance frequency. And you can see it has the inductance that electrically we can do nothing about, but it also has the capacitance and capacitors are tunable, and this is how the resonance frequency of the probe is tuned to the Larmor frequency of the precessing nuclear spin, and so our instrument can transmit and receive that frequency unimpeded, which is the role of this matching capacitor here, and finally we will get the signal. And what we do with that signal is the next lecture. Any questions?